Real good. Feels really good. All right, nice. So let's take a look at this quick little simulation here on stationary waves. I'm going to show you how they produce it, right? One of the things with stationary waves, unlike other waves, it does not transfer energy, right? There is no transfer of energy. That's why it's considered stationary. All you have is the energy that's moving it from one point up and down. You're not transferring it from one point to the next. Right? So let's take a look at the stationary wave. Hold on, I'm not seeing it. All right, standing waves, right? That's what they call it, standing waves. All right, so look here. If you take a look here in this simulation, what you will see, right, we're going to make it oscillate. Hold on. Right. Here you have a string. The string is fixed at one end, right? One end of the thing, one end here is fixed, right? So nothing will oscillate at that point. See that green dot? Nothing will oscillate there. Right? If I were to send a pulse, I wanted to watch what happens to the pulse. See if you could tell me actually what is happening to the pulse here. So I'm going to move the string up. Right? Let me just remove the tension. Right? Watch what happening to you there. It's a little delayed, it's slightly delayed. What happened to the wave as it hits, as it reaches this point here? Anybody can tell me what happened to it? Right, let me just take off the damping, right? What happened to the wave as soon as it hits the fixed point, right? It changed direction, but something happened. There's a reason why it changed direction. It happened at all the fixed points. Anybody recognize that? What do you call that phenomenon? Look at going to meet the green again, and then something happens on top. That's called reflection, right? When the wave hits there, it reflects underneath. Okay, so it's reflected. Now look at what I'm going to do. I'm going to send two pulses. Tell me what you recognize when the two pulses interact. You'll see a little superposition. When those two waves interact, it have a little bit of superposition. It's a little delayed on some people, right? But what you see happening there is the superposition of a wave, right? Let's take a look at the oscillating now. When the oscillating wave hits the fixed point, it will reflect. You're seeing a larger wave being produced there. Those who online, actually not a little. I've seen a little bit of lagging, but you'll recognize that the wave that's being produced is larger. Look how much larger there. You see it good, right? It's much larger than the initial wave. Those waves being produced, they are called stationary waves. Right? So when the reflected waves superimpose, you have a stationary wave being produced. If I were to adjust the frequency, I can control the amount of waves you actually see it. All right. You mightn't be able to see it because some people would have it a lot, but there are points there that are not oscillated. Those points are called nodes. All right. So basically, that's the stationary wave there. If I drop the amplitude and drop the frequency a little more, I'll drop it a little bit, right? I just want to show you now. I drop the frequency. You're still going to get the stationary wave, but you're not going to get as much. Right? Here you're technically only getting 1, 2. You all see enough? See those points here? It's moving a little bit, but those points there of maximum displacements, those are called antinodes. Right? Those points, they are called antinodes. And the points in the middle where there's barely any displacement are called nodes. All right? So you have a little idea. I'll send the video with the guys' simulation. It's perfect. It shows you exactly what will happen, right? By adjusting the frequency, I can't really go much lower, but by adjusting the frequency, I could control the type of stationary wave being produced. So in a way, I'm kind of controlling the amount of antinodes being produced. Right? A practical example of a stationary wave is like if you were to blow into a bottle and you hear a loud sound, that loud sound that you're hearing is a stationary wave. And if you adjust the frequency, right, you'll be able to hear well at different loudness, right? Anybody here ever did a tune-in fork lab? Ever tune-in fork? Right. What you're hearing there are stationary waves. The kind of loud sound that they're hearing, that's stationary waves. All right. I wish I could have shown you the video, but see if I could anyway, I'll look for the link and I'll share it with you, right? Right. So stationary waves basically as a result, right? You have a wall, you have a wave. When that wave hits the wall and it reflects, these two waves, they superimpose on each other and they produce a large wave. That larger wave is a stationary wave, right? A stationary wave is generally drawn like this here. So you could draw a stationary wave like this. Right? The reason you draw it like that is that the wave is oscillating between these 2 points here. Right? So at one point in time, the wave like this, the next point in time might be the other way around. All right? So that's the way you draw your stationary waves. Right. There are some important things that we need to learn about a stationary wave. Stationary waves have points that do not move. Right? Those points there, those points are called nodes. So all those stationary points are called nodes. And then there are points that will undergo maximum displacement. Those points are called your antinodes. Right? Antinode to antinode is how much? Anybody can tell me based on that diagram there? Antinode to antinode is how much of a wave? Here to here. Half a wave. Nice. Half a wave. Right? Remember the diagram we looked at last week? Yeah, last week. We said from here to here is 1/4 of a wave. Here to here. Here to here will make it a half. Here to here is our next quarter. So that's 3/4 of a wave. Here to here is a whole wave, right? So basically from this point to this point, antinode to antinode, that's half of a wave. Okay, so you need to be able to watch a wave and identify, okay, that's quarter, that's 3/4, so on, right? Right, so how many antinodes do you think will make a wavelength? How many antinodes do you think will make a wavelength? Antinodes, huh? Gotta be careful. It won't be 4, it will be 3. What you say? If I were to draw one more antinode, there's half and here's half. Right? So it will take 3 antinodes to make a whole wave, right? Okay, nice. So we learned the features of our stationary waves. Everybody okay? Sarah, are you okay? Louis? right? So those are the features of a stationary wave, right? Lewis, did you do it myself, right? All right, nice. So now, how do we know the type of stationary wave being produced? As I told you before, if I were to adjust the frequency, I could control the number of antinodes we see it. But remember that? In the simulation, if I were to adjust the frequency, I could control the number of antinodes, right? So therefore, here's how we can work it out, right? Let's see, let's start with our first example. We have two, well, it's in your notes earlier, but that's kind of going it over, right? Two fixed ends. If I have two fixed ends, it simply means that, right? Two fixed ends, it basically means that I have a node here and a node here. Two fixed ends means no displacement will happen there, right? No superposition. At your first frequency, let's call that frequency F0. Here's what you're going to observe, right? If you look back at this wave, right? Between your first two antinodes, between here and here, how much of a wave you are being produced? Between your first two nodes, sorry. How much of a wave you are being produced there? Right? That's half a wave. Here to here is half a wave. Two nodes, right? So between the first two nodes, what you have there is half a wave being produced. So this stationary wave you see in here, which occurs at F0, is called your first harmonic, right? That's the first, like if you all do the one with the bottle and you're blowing it at that frequency F0, that'll be your first harmonic. Some books have it as your fundamental, frequency or your fundamental stationary wave. Okay, so your first harmonic looks like that, right? With two nodes on either end and with nothing in the middle. If you were to further adjust the frequency, let's say you increase the frequency to F1 now. The type of stationary wave that being produced, that'll be a second harmonic. I want to show you what your second harmonic will look like. You have a node here, you have a node here. That's not changing, right? So your second harmonic will now look like this. So you're increasing the frequency. So your second harmonic looks like that. Right? Because you must always have a node on one end and a node on the next end. So basically, if you look back at the original, we have a node here, a node here. The next time that we could get two nodes on either end is here. How much of a wave is that? Between those three nodes. A whole wave, right? See that? A whole wave being produced between those three nodes. So if you look here, when you adjust the frequency to F1, you will end up with three nodes or a whole wave. Here's half a wave, here's a whole wave, right? What you will recognize as you go from one harmonic to the next, it's increasing by half a wave. So since you know that now, anybody could guess how much of a wave we will have between these two nodes if I go to F2 for your third harmonic? Online, what you all think? Lewis, what you think? If I move to my third harmonic now, how much of a wave do you expect to see there? With two fixed ends, right? Anybody else could suggest as well? Per, what do you think, Per? Right, good job, Eden. Good job, Karina. Per, what do you think? Yeah, correct, I'm Chelsea. Correct, Jude. Lewis, what do you think there? Since we keep adding on half a waves, then we should get something like this, right? You gotta be careful earlier, so you want to fit 4 nodes now, right? So it will be 1, 2, sorry. 1, 2, 3. It will look something like that. 1.5 waves. Right? 3 lambda and 2. Are you okay with that? Very, you are not very. I'm gonna stop recording this way. I'm gonna stop recording there. Harris, you okay with this? Harris, you there? So these are the 3. Okay. So these are the 3 waves that you should expect to see starting from first harmonic to third harmonic. Right? Of course, fourth harmonic will be how much? 2 waves, right? Right. The good thing about this is that we can actually predict the frequency that F1 and F2 will happen at. Right? Here's how you can work it out. Let us say it's a string we're using, right? Like the example I showed you. And the length of the string from this node to this node, the length of the string is L. And it's moving with a velocity V. We can predict the frequency it will happen at, right? The length is L, right? Watch this here. We can predict F0. So I'm going to do a small calculation here for you, right? So lambda 2 is equal to L. In the first example, you're seeing that? It's half a wave and equal to L. So it means that lambda is equal to 2L. Yeah? So that means that if I were to find F0, remember V is equal to F lambda. F0 will be V over lambda. Well, V is the same value for all, and lambda is equal to 2L. So F0 is V on 2L, right? Let's see what's going to happen for F1 now. As I said before, for F1 is a whole lambda is equal to L, right? This here is equal, it's the same string, right? It's the same string, length L. It's just now all are being produced here as a whole wave. So lambda is equal to L. So therefore, look at what happens to the formula. The formula for F1 is equal to V over lambda, which is V over L. Or we can multiply 2 by F0. Multiply 2 by F0. If I multiply this by 2, you will see again V on L, which is F1. Recognize that? So if you had to guess, what do you think F3 will be? Sorry. What do you think F2 might be? Anybody can guess? F1 is 2F0. If you had to make a guess, what do you think F2 might be? In terms of F0. 3F0, yeah, that's a good guess. I think good. Can I make a guess for F2? 2.5. Let's see. Online, what you all think? Sarah, what do you think F2 will be? 3, okay, 3. So let's see, right? So as I said here, 3 lambda and 2 is equal to the whole length of the string. If we rearrange this formula, you'll get lambda to be equal to 2L over 3. So if you try to find velocity, if you try to find frequency is equal to V over lambda, which is V over 2/3 L. If you rearrange the formula, you will get 3V over 2L, which is equal to 3F0. Right? Remember, this here is F0. So you'll get 3F0. So the third harmonic will happen at 3F0. What about the fourth harmonic? It will happen when? 4F0, right? And so on and so on. Okay? So by adjusting the frequency by F0, we can move from first harmonic to second harmonic to third harmonic. All right. Any questions online? Louis, any questions? Rika, any questions? Shabani? Any questions, Shabani? All right, so these are your harmonics here for two fixed ends, means two non-oscillating ends. What I'm going to ask you to try from now, we're going to make one end open, one end free to oscillate. Right? And then we're going to try and draw it, right? So we leave in one end fixed. So there'll be a node there. So this is one end fixed. What do you think will be on the next end? What do you think will be on the next end? If it open and it's free to oscillate. Would it be a next node or antinode? Antinode. Right, very good. Antinode. Right, so I have a little problem here now, William. Node to antinode. So there's an antinode up here, right? So the wave will look something like this, right? Correct? How much of a wave is that? How much of a wave is that? Quarter of a wave, right? Online, you'll see that there's a quarter of a wave. If we go back to the first diagram here, node to antinode is 1/4. Okay? So that's quarter of a wave. Right? So quarter of a wave now happening with the whole length of the string, or right? The whole length of the string, but remember one end open, right? So when one end fixed and one end open, the first harmonic looks like that. That's your first harmonic there. So your first harmonic is lambda 4 and L, so lambda is 4L. So therefore, F is equal to, well, F naught. F naught is equal to the velocity oscillating at all over lambda, which is 4L. That's the F naught, right? Do me a favor. Draw your second harmonic and third harmonic. Draw your second harmonic and your third harmonic and tell me what you get for F1 and F2. Try that, please. Right, try and draw the second and third harmonic. Right, so try and draw your second harmonic and your third harmonic, right? Let's see how it looks, right? And then see if we can find F1 and see the relationship. Right, already? Yeah. Back at your first diagram, right? Yeah. So look for the next separation where you start with the antinode and finish with the node. Okay, try and draw 3 harmonics, right? Right, so you can look back at the original, this one here. If you look back here, Look for the next time that you start with an antinode and finish with a node. So the first time I drew it for you already, look for the next time here. Right, so you're starting with an antinode and you're finishing with a node. How much you think you from first harmonic to second harmonic? How much your weight increasing by? Jude, how much is increasing by from first harmonic to second harmonic in this case? Right, half, very good. So it looks something like that. So you would recognize that it keep increasing by half a wave, right? So that's a golden rule. One harmonic to the next always increases by half a wave. Okay, right? And then you can work it out. You have 3 lambda and 4 because now you have a 3/4 of a wave in front of you. So 3 lambda and 4 is equal to the entire length of the string. So lambda is equal to 4L on 3. So F1 is equal to V over 4L on 3. Flip it over, do your little maths, you'll get 3V over 4L, which is equal to 3 by F0. Right? This is your first harmonic, this is your second harmonic. Right? If you had to guess, third harmonic is what? How much F0? Right, good. We'll work it out. Same different answers. Nice. Work it out. So a third harmonic, right? Node, antinode to node, the antinode to node. Right, mine didn't come out 200 right there. This pen keeps slipping. So it looks something like that, right? So you add a next half a wave. So that will be when you add a half to that, that will be 5 pi on 4. This L lambda is equal to 4L on 5. So F2 will be V over 4L on 5. So that would be equal to 5 over 4 V on L, which is 5 F0. Right? So you went from 1 F0 to 3 to 5. Next one will be what? 7, right? Following pattern is 7. Nice. But the most important thing is you should be able to draw them, and you should remember that all harmonics increase by lambda and 2. This year, you don't have to learn this off, right? You can work that out. All right, but you have to learn how to draw them. Okay, so that's your first harmonic, your second harmonic, third harmonic for one end open. Right, let's go to the handout quick, and then we can start doing the questions on this, right? Any questions there, Fer? Right, so we have these stationary waves being produced, and these stationary waves are basically superimposed waves, right, that have the same amplitude and same phase and same velocity. All right. Let's go back to the handout here quickly. Right. So you have a little note here on stationary waves, right? They talk about node and antinodes and so on. Here we have the simulation, something like the simulation that we did. This here was your fundamental for 2 fixed ends, right? This is your second second harmonic, right? First harmonic, second harmonic. This here is a formula that we could use to find speed of the wave, right? Tension in the string divided by the mass per unit length, square root of that, right? Right, here we have it for, we did this one, fundamental and first harmonic and second and third, right? This is for one end open, and these are the calculations here. Now, if you have both ends open, that's the way to look. And the reason for that is, oh gosh, I can't write. The reason for that, why it looks like that, I can't write. So let me see somebody can help me. Anybody online can help me out there? Aidan? Shivani? Why it looks like that? Both ends open. Shivani, why that happen there? Right, remember that both one end closed look like this. One end open, one end closed. What happened here? Shivani, what we have being produced on the ends? Right, so we have antinodes being produced, right? Because there are no fixed points, so they're free to oscillate. So at those points, yeah, you have your antinodes. Remember, this mightn't happen with a string, it might happen with air, right? So you have your two antinodes on either end, right? And well, the calculations there. Right? F naught, right? F1 is 2 F naught, F3 is 3 F naught, and so on. Right? And you have some examples here of stationary waves, right? Well, we could always read up on that, right? Let's try a few calculations, right? I just give me 1 second, get the booklet, right? Right, for those who write it down, you put this to my favor now, add that in now. Right? You'll need that formula there. P is equal to the square root. Yeah. Louis, send my WhatsApp and I'll add it to the group. Yeah, with 1 second. I see there are some questions now on stationary wave, right? You will need some of this little foundation, right? We'll get one from here before I give you a class paper. You are passing. Taking this off, right? So let us start. Right, let's start with one that's a little easy, right? Just to give us an idea of how it works. All right, so let's say we have first one, right? Let's use sound, right? So let's say I gave you the speed of sound. The speed of sound is let's use 330 meters per second, right? And I'm giving you a tuning fork. A tuning fork is a device that is used to produce frequency, right? Let's say the frequency is about 100 and is now we multiples of right 120 hertz, right? I would like to know, let's see if we could find the length, of the string. Find the length of the string. Sorry, I write that bad, right? Find the length of the string at your first harmonic. Right? Let's assume that we had two fixed ends, right? How are we going to get the length of the string here? Since it's two fixed ends, right? Since it's two fixed ends, here's a node and here's a node, right? How big will the wave look? How big the wave will be? How long will it be? Sorry. It'll be half a wave, right? So from one node to one node here, it'll be half a wavelength, right? Because remember, it's two fixed ends, right? So this is lambda on 2. So lambda on 2 will equal to the length of the string, right? Correct? So if I ask you to find the length of the string, what we need is lambda on 2. How do we get lambda? We have speed, we have frequency. So what that means is that lambda is equal to V on F. Right? V is 330, and here's 120. How much is that? Check it for me now. You have a calculator? How much is lambda there? 2.75, right? Yeah, 2.75. So it means that the length of the string is 2.75 on 2. Right? That's the length of the string. How much is that? 1.375. Right? That's the way that we could find the length of the string, right? Any questions there, Olia? Are you okay with that? Are you okay with that? What do you rest of it? What's this next fellow name? Anyway, I'll be coming next week. What do you Pressman has come basically? Yeah. Or for Aiden and Judah. Yeah, the next fellow name. Yeah. Any questions there, Olia? Rika, you okay with us? Where can you see test on Chisino? What's up? Shivani, there still? Zaria, are you okay? All right. Let's change it slightly. Here's what I'm doing this time, right? All I'm telling you that giving you a string. I'll give you the length of the string. Let's say the string is 1 meter. Right? at second harmonic, the frequency is 220 hertz. All right, do me a favor now. See if you could rearrange all of this. So at second harmonic, right? Both ends fixed. Here's a node and a node, right? At second harmonic, the frequency is 220. See if we can find the speed now. See if we can find the speed of the string. How you pronounce your first name? I didn't remember that. You're good with George, right? I tried to remember last time and I know I called it Duncan someday. Yeah. Louis, send my WhatsApp tune up, please. I'll save a number. Let's spell it again. A-B-A. Wait, I thought I saved it as now. A-B-A, yeah. Right, message answers. So I think you have it. Take your time, of course, to find, you know the formula for speed of a wave, right? So you'll figure out what you need to get. Remember, it's second harmonic and both ends fixed, right? All right, I have one answer so far. Louis, send my WhatsApp now, please. Right, message your answers. Let's see what you got. Baby. Right here, I'm missing the thing called answers there earlier. I have one person so far. What you get, Jude? I mean, Sean. So for your second harmonic, how big will the wave be? Your second harmonic looks like this, right? Well, with two fixed ends, you'll end up with an entire wave. You'll end up with L being equal to lambda. Right? So at your second harmonic, what you're going to see is a full wavelength. So it means that L is equal to lambda. So therefore, lambda is equal to 1 meter. So it means that the speed of the wave is f lambda, frequency is 220, lambda is 1. So your answer is 220 meters per second. Right? Problems there earlier. I only got 2 answers. Well, 3. Reggie, good job. Jude, good job. Karina, problems? Sarah? Zaria? Why didn't you send the answer then earlier? Sarah, why didn't you send the answer? It was sent it still. All right. Next one. Let's do one more, I guess, before I jump into our past paper, right? It's all right if I think all wrong. I wouldn't say anything. Oh, let's try to fix it. Let's see. So we have that. We have that. All right. I feel like I can handle the past paper. Right. I can't remember the years, right? One is 2004 and one is the one before that. Try this here from now. It's a little bit harder. Same concept though. Same concept, right? I don't know if you all did that lab already, right? But try this one for now. All see it? See it? I want to think you have your answers. Splendid, please. Where? What are you doing there, boy? I'm partner as them. Have a part A, but we've been anyway. Something I had to remember there. One of the key things I told you to remember when you're going from harmonic to harmonic. Right? When you're going from harmonic to harmonic, something happens. Right? Enhanced meaning it was high, right? So you had a stationary wave at 0.6 and then at 1. Don't matter. That don't matter. Technically, yeah, but that don't really matter. What happens from one harmonic to the next? Of online, anybody remember? When you go from one harmonic to the next, what happens? Very good, Karina. Anybody else? right? So that's what you have to remember here. When it went from 0.6, we don't know which harmonic it is, to 0.1, right? That was two consecutive harmonics. So as it go from one harmonic to the next, it increases by half a wavelength. That's supposed to help you, right? Supposed to help you. I hope it does. Not helping you? There, right in front of you. Socially two most of them. Why trying to find? How you find speed? Right? What's the frequency? Right? So you have to figure out what. You gotta figure out lambda, right? Right, don't you? Right, those who online try it, message your answers. Please, even if you think it wrong, I wouldn't call your name. I won't say anything, right? So you're trying it. Jude, check it over there. I'm looking wrong. Who? I'm take a shot. It's that's why I do wrong. Huh? That's it. Become a sim. Try back one more time. Any more answers online, Olia? Right, Jude as much. That looks more like it, Jude. Right, message your answers, Sarah, Karina, Shabani. All right, good. Let's see what we have here. It's not the people who don't want to send anything. So for me, if I were doing this question, they want me to find speed of sound, right? I know that speed is equal to F lambda. Frequency is equal to 440 hertz, right? I don't know lambda, so I have to figure out lambda, right? The only bit of information I have here. No, that's not coming. Right, sorry there. So yeah, so we need to find lambda, right? We know that from one harmonic, it doesn't matter the harmonic, from the nth harmonic to the n plus one harmonic, right? It's half a wave, right? Half a wave will be introduced there, increased by half a wave, right? So it means that half a wavelength is equal to 1 minus 0.6, which is 0.4 meters. So a whole wavelength will be 0.8 meters. Therefore, the speed will be 440 multiplied by 0.8, which is 352 meters per second. You guys know? Huh? Right? So it's 352. Oh, okay. Right, so let's take your time and work it out, right? Are you okay with it now, Karina? Or let's send the answers now, please. I just want to have an idea how are you doing. Saria, if I ask you now, yes, you will say, yeah, you're okay. Let's do one more now. Please send the answers. Copy them. So again, generally, this is the way you answer questions, right? You write down what you have to find and any formula or relationship you know. Then write down everything question give you. Then you would recognize, well, I have frequency already. I have to figure out now how to get wavelength, right? So then you look back at the other little bits of information and see how you can figure out, okay, how is this going to help me find wavelength? Question said there was an intensity. There was an intensity at 0.4 to 0.6. Sorry, 0.6 to 1, right? So that's one harmonic to the next. They didn't tell us which harmonic. All we could figure out here is that from one harmonic to the next is half a wavelength. And then you do your little working and figure it out, right? Right, so please learn to break your questions down like that, right? One more. At least do part C. Forget part D. Part D is using the formula I gave you. See if we can figure out part C. Part C tricky, yeah? Part C is a little bit tricky. Right, so you had to figure out part C now. They want you to find the lengths at which your tuning fork, right, will produce resonance. All they're talking about is a next term for resonance is the superposition of waves, which is your stationary waves, right? What you have to remember here is one enclosed, and they give you some values there. So see if we can figure out what lengths between 0.5 and 1.8, you'll be able to hear these stationary waves. Right, so you have to figure out now what you're gonna do. You have speed of sound there and you have frequency. Right, the length, the one at what lengths. So they could adjust the length, right? Right, do the usual things, right? Write on what you know the speed, which is 340. you know the frequency. So if you know these two things, what you can easily find. Sean? Sean, you have the ITSB to do as well, you know that, right? You went to any IT classes? What you can easily find here. If you have V and F, the wavelength, right? So the wavelength is V over F, which is 340 over 280. Oh, how much is that? Right, nice, Shivani. 1.21. Okay, good. So we can easily find the wavelength, 1.21 meters. Good. Do you think? When would you be able to hear it? At what lengths? Well, some of you will figure out one already. Check out if we could hear it again now. Right, one end open. One end closed, one end open, right? You'll kind of figure out one already. Right, you'll calculate the lengths. Question said lengths, so there should be more than one. Right, Chelsea figured out two of them already. Good job, Chelsea. Any more, Chelsea? How much you have? Two alone and three or four? How much you got? Chelsea only have two. How much you got? Two. How much you got, Brandon? Andy, how much you got? Wait, Chrissy didn't come today. Andy, how much you got? All right, so let's start working it out. Still working. So we know lambda is 1.21. So we might be able to hear it there. Let's see. So one end open, one end closed, right? So let's check out here. We know here's quarter of a wave. That's our first harmonic. At quarter of a wave, how much is that? 1.21 over, oh, let me just write the range here, right? The range is between 0.5 and 1.8. All right. So 1.21 over 4, how much is that? 0.3? Okay, so we're not going to hear that. We're not going to hear there, right? We're not going to hear there. We know they all increase by half a wave, right? So let's add half a wave. One whole wave is 1.21. So half a wave is how much? 0.6 what? Let's average, right? 0.61, right? Good. So let's add half a wave now. So we add in 0.61 to 0.3. Our second harmonic will be heard at 0.91. Is that in the range? Yes, we got two, right? So it's between 0.5 and 1.8, right? Andy, you okay with that? Then we're going to add half a wave again. So we're going to add 0.61. How much is that? 1 point? 1 point. Later. 1.5. Well, if I use my value, 1.52, right? Good. So we're hearing it at 0.91 and 1.52. All I'm doing is just adding a half a wavelength, right? Nothing else. Just adding half a wavelength. Okay, from one to the next is half a wavelength. The first one, we're not hearing it because it occurs at 0.3. When you add half a wavelength, it's going to 0.91, we'll hear that. Let's see if we'll hear, so we're hearing the second and third. Let's see if we'll hear the fourth. So let's add 0.61 again. How much is that? 2.13 or something. So you will not hear that. So our answer will be at 0.61 meters and sorry, I write the wrong thing. 0.91. We will hear it at 0.91 meters and 1.52 meters. Right, so we'll hear the second and third harmonic. Are you okay with that? Serious? So you had, how much you had? You had two of them, okay. You had two of them. But let's see what you did. Right, remember you're starting at quarter of a wave and you're adding half one, right? Are you okay with that? Yeah? Chelsea, I said Sarah, I meant Chelsea. I saw a little mistake, right? Sarah, you were good, right? Everybody okay with that? So remember, although 1.21 looks like it in between 0.5 and 1.8, if you look here, there is no whole wave here. This is quarter wave, 3/4 wave, 5/4 wave, right? There is no whole wave, right? Between one end open and one end fixed. Okay, so you really needed to figure out the first one and then half a wave, and you can keep adding it on. You're okay with that there? Right? It started as a quarter wave, and that was the important thing. You start from a quarter and you keep adding the half wave on. Okay, that's why it's important you know these diagrams. If both ends open, you're starting at half a wave. If both ends close, you're starting at half a wave as well. All right, and you're always increasing by half a wave as well. Okay. All right. Nice. Any questions online? Hello, okay there? Saria. Hey, someone do respond at all.